A robotic camera lens tracks across an empty room as a local processor dynamically maps every surface with digital wireframes in real time. For years, the industry focused heavily on virtual reality. VR is an enclosed system. It completely blocks out physical surroundings, replacing your visual and auditory senses with a simulated environment. This graphic shows the core difference. VR operates in a simulated space, while augmented reality uses a 75% real to 25% virtual ratio. In AR, you maintain continuous physical presence. On the left, digital data overlays the physical environment, distinguishing real from rendered. But creating that overlay is incredibly difficult. An AR application isn't a static filter snapped over a photograph. It is a highly constrained, continuous computational loop that has to refresh dozens of times every single second. We map that loop using this system flowchart. The pipeline begins at the input nodes. A camera ingests raw visual data from the real environment. This routes into a computer vision module, merging with virtual objects, then composites into an augmented scene for the display. True augmented reality operates like a house of cards. If any single node in this continuous pipeline drops a frame, miscalculates depth, or lags, the entire illusion collapses and the user experiences immediate disconnect. The most demanding computational bottleneck in that pipeline is spatial tracking. Forcing a machine to understand its exact position and orientation within a 3D space requires intense processing power. The most reliable tracking method engineers use is marker-based AR. It offers extremely high spatial accuracy with a very low processing footprint. A marker-based system relies on the camera detecting predefined high-contrast visual anchors, like black and white QR codes. Once the camera registers the pattern, it triggers the digital asset, anchoring it directly to that specific physical marker. The strict limitation here is environmental preparation. Because it requires physical markers placed in advance, this tracking method is entirely useless outdoors or in unpredictable dynamic environments. To achieve macro-scale outdoor tracking, the system relies on location-based or markerless AR. Instead of scanning for visual patterns, a markerless system pulls raw telemetry data directly from the device's internal GPS, accelerometer, and compass. By calculating the device's exact geographic coordinates, the system can pin digital assets, navigation paths, and informational labels directly onto physical city streets. But relying on GPS and gyroscopes introduces drift. Markerless AR lacks the millimeter-level micro-precision necessary for complex, close-range indoor tasks. For precise local environmental mapping without printed markers, the hardware uses superimposition-based AR. Superimposition requires constant, advanced spatial awareness. The computer vision module has to instantly detect flat planes, map physical boundaries, and handle object occlusion so that a digital armchair anchors logically to a real floor rug. Selecting a tracking taxonomy always requires an engineering trade-off. You can prioritize the macro-scale freedom of GPS tracking or the absolute micro-scale accuracy of a physical marker, but current technology forces you to choose. Once the computer vision module successfully tracks the environment and composites the digital objects, that final image has to be physically delivered to the user's retina. This chart breaks down the display hardware taxonomy, mapping the evolution from standard consumer mobile screens up to enterprise-grade wearable visors. Looking at the bottom row, head-mounted displays provide a completely hands-free experience. This is a strict requirement for high-stakes applications like industrial maintenance or surgical visualization, where the user needs both hands available to work. But head-mounted displays face severe physical limitations. Hardware engineers are forced to pack multiple processors, high-capacity batteries, and complex optics onto a user's face, while keeping the weight low enough to prevent neck strain and visual fatigue. Handheld devices like smartphones and tablets bypass those wearable limits entirely. However, they reduce the user's immersion to a restrictive magic window effect. Despite a limited field of view, handhelds offer massive utility for immediate, highly accurate tasks like spatial measurement and real-time room mapping. Regardless of the screen type, moving AR from a passive viewing experience to an active tool requires two-way interactivity. Integrating advanced spatial UI design allows for hands-free gesture recognition. Users can interact with virtual content entirely through specific hand movements, completely eliminating the need for physical touchscreens or external controllers. Ultimately, display hardware remains the absolute bottleneck. The tracking algorithms can be flawless, but the user's experience is strictly bound by the thermal limits, battery density, and optical weight of the physical device. Rendering a single 3D object for one user locally is already a hardware strain. Attempting to share that exact same object in real time with multiple users in a collaborative space multiplies that strain exponentially. The network penalty is severe. Streaming a standard 720p virtual reality video requires a reliable 50 megabits per second. Interactive augmented reality demands upwards of 100 megabits per second just to function. This bandwidth surge comes from the nature of the data. The system must transmit dense spatial coordinates and point cloud maps rather than static video pixels. If the network drops packets or lags, the system misses its refresh cycle. Even a few milliseconds of processing delay will cause frame drops, breaking the user's immersion and inducing motion sickness. Overcoming this latency requires a specialized architecture, known as a multi-user cooperative AR system, or MUXIS. This diagram illustrates a standard MUXIS architecture. It acts as a central data hub, synchronizing entirely different user roles, from designers and salesmen to on-site inspectors, into a single shared spatial layout. The latency stakes here are absolute. If the designer edits a layout on a desktop, that spatial calculation must instantly process through the hub and render correctly inside the inspector's headset standing on the physical factory floor. When you add advanced features like haptic feedback, which calculates and simulates physical textures and resistance when touching virtual objects, you push these data processing requirements to the extreme edge of current network capabilities. True real-time collaborative AR is a strict networking challenge. Rendering high-fidelity graphics is largely a solved problem. Defeating latency across a shared physical space is not. With such tight computational margins, engineers evaluate an AR system based on strict, measurable performance metrics rather than aesthetic polish. System engineers evaluate success based on concrete data, task completion time, tracking stability when a room's lighting drops, and how accurately the system handles digital object occlusion behind physical barriers. Returning to the foundational blueprint, we can trace exactly where these metrics are tested. During the input phase, the hardware must flawlessly capture raw environmental data without dropping frames and successfully pass it to the computer vision algorithms. During the output phase, the system has to composite those complex data streams with zero noticeable latency and display them on hardware that doesn't trigger cognitive overload in the user. Scaling this architecture introduces massive ethical constraints. AR requires cameras to be on constantly, continuously mapping the real world. This creates extreme data privacy risks and enables passive, continuous surveillance. Furthermore, the industry faces severe software fragmentation across multiple development kits, keeping hardware costs high and slowing widespread adoption. Mastering this real-time computational pipeline is the final requirement for spatial computing. Once latency and hardware limits are resolved, digital infrastructure will leave the flat screen behind entirely, anchoring data directly into the physical space around us.